Welcome to Mr. Luchesky's lesson on chemical bonds. This is section 2, bond energy and covalent bond strength. So, in forming a covalent bond between two hydrogen atoms, energy is released. This is the same amount of energy that has to be added to separate the bonds. So, engineers understand this idea that if you want to see how strong something is, you break it. So what energy that it takes to break a bond between two hydrogen atoms is the bond energy. And that's also the energy released when two atoms form a bond. So the energy that it takes to break it is the same as the energy it takes to make it. All right. Now the distance between the bonded atoms at their minimum potential energy, that's the average distance between two atoms, is called the bond length. Okay, so here is a chart that shows you bond energies and bond lengths for a number of different common bonds. So, for example, the bond between the hydrogen and fluorine atom, that bond energy is 570 kilojoules per mole. In other words, to make a mole of these, or to break a mole of these bonds, would require 570 kilojoules. Okay, so we're talking about bond energy. Well, another word for bond energy is bond enthalpy. So the bond enthalpy is the same as the bond energy, which is indicator of the bond strength. And the strength of the bond, of course, is measured by the energy it takes to break the bond. So the strength of a bond is also called the bond enthalpy, and it is determined by how much energy is required to break the bond. Okay, so here is a chart of bond energies for a lot of different bonds. So, for example, the bond between carbon and hydrogen. To break this bond would take 413, look at the units, kilojoules per mole. All right, so these are averages. Now, notice something, that these average bond energies are positive because breaking a bond requires you to put energy into it. It's an endothermic reaction. You have to use energy to break that bond. And where does that energy go? It goes inside the atoms, right? And when typically, all right, when atoms form or when bonds form between isolated individual atoms, all right, it gives off energy. Now, notice that the bond energy, these are average bond energies, because not every bond in nature for a pair of atoms has exactly the same bond energy. Okay. Now, we can use these bond energies to estimate the delta H, the enthalpy change for a reaction. So you've got bonds that are being broken, and then that requires energy. Then you've got bonds being formed to make the products, and that returns energy. Okay, so the formula we use for the change in the enthalpy, delta H RXN of reaction, is the sum of all the broken bonds. That's what this symbol means. Sigma means sum of everything in parentheses. So sum of the energies or enthalpies of all the broken bonds. And from that, subtract the sum of the enthalpies of all the bonds that are formed. All right, so here's a typical reaction. You've got methane reacting with chlorine gas, and it forms methyl chloride. That means you've got, notice here you had 4 hydrogens, and over here you only have 3. So one of the hydrogen bonds to the carbon is broken, and a new bond is formed between the carbon and the chlorine. And before that can happen, these two chlorine atoms have to be split. So the bonds have to be split so that one of the chlorines can attach to the methyl and the other one can go to the hydrogen. So let's take a look at this in terms of bond energies. So you've got your first bond here that's broken. Is one of these hydrogens is all the hydrogens are bonded to the carbon, but one of those bonds gets broken, and that requires 413 kilojoules of energy per mole. The next bond that's broken is between these two chlorine atoms. That bond is broken. Oh, we use the D in parentheses to stand for the enthalpies, by the way. D followed by a bond represents the bond enthalpy. So this was the bond enthalpy for the carbon-hydrogen bond. This is the bond enthalpy for the chlorine-chlorine bond, which is, according to the chart, 242 kilojoules per mole. Now, on the other side, we have a bond being formed. All right, this chlorine took the place of a hydrogen, so you have a bond, and it's bonded to the carbon. So this carbon-chlorine bond has an energy of 328 kilojoules per mole. The other bond that's formed is this one here between the hydrogen and the chlorine. All right, and that bond energy is 431 kilojoules per mole. So how do we add these up? How do we do with this? All right, so here's a diagram that depicts a drawing that depicts what's happening here. So here's your CH4. That's the carbon. These white spheres here represent the 4 hydrogens. Then you have a chlorine molecule. Here's a chlorine atom bonded to another chlorine atom that makes up the chlorine molecule. So the first thing that happens is one of these bonds is broken. Let's just break this one here. They're all identical, so it doesn't matter. But let's break this one here. So when that happens, you have to put energy in. The energy goes into the molecule. So this thing here, this methane, has less energy than the split hydrogen and methyl group. So that's why it's higher in this chart. See that as you go up the y-axis here, that's a measure of the energy or the enthalpy. And time, as the reaction occurs, is along the x-axis. So this is what happens first. These things split up. Then the chlorine splits up. And the chlorine atoms individually have a greater energy than the chlorine molecules. That's why it's up here in the higher chart. But how much? What is the change? What is the delta H, the change in the enthalpy here? We're going to put numbers on this in just a minute. Let's look at the other side of the reaction. So, as products form, one of these chlorines will now bond with the methyl group and form this thing right here, the methyl chloride. This is methyl. CH3 is the methyl. And that's chlorine. So this is the methyl chloride. All right, now the other hydrogen here is going to combine with the other chlorine and form HCl. That's H, the hydrogen, and that green sphere is the chlorine. All right, so, whoops, back up. All right, so let's take a look at the energies here. So for the first step, we're going to start all over again. This bond is broken between the carbon and the hydrogen. And that bond enthalpy is 413 kilojoules per mole. You looked that up in the chart on the previous slide. The next bond that's broken is this chlorine-chlorine bond. So that bond enthalpy, see, between the two chlorines is 242 kilojoules per mole. So that's how we split up the chlorines. Right? Now on the other side, you've got this methyl group attaching to the chlorine, and that forms this thing down here, and that energy released. Now, if energy released, so this methyl and this chlorine are up here in the chart. They have high energy level. All right, once these bonds form, this compound now has a lower energy. That's why it's lower in the graph. See how this works? By how much, you might ask? By 328 kilojoules per mole. Now, the other thing that's going to happen, the last step, is this hydrogen will react with the chlorine way over here, right, and then form the hydrogen chloride molecule. And that gives you back 431 kilojoules per mole. All right, so let's do the math here. So we've got the carbon-hydrogen bond. The D means the enthalpy. So this is the enthalpy of the carbon-hydrogen bond. We add that to the enthalpy of the other bond that's broken, the chlorine-chlorine bond. We add these two together. That's why it's in these square brackets. Then we go over here and we take the energy of the carbon-chlorine bond that's formed, add that to the energy of the hydrogen-chlorine bond that's formed. The sum of these two is then subtracted from the sum of the first two. All right. So the carbon-hydrogen bond is 413. I'm going to put that right there in just a second. The chlorine-chlorine bond is 242. That goes right there. The carbon-chlorine bond over here is 328, and the hydrogen-chlorine bond is 431. So let's put the numbers in. Carbon, hydrogen, 413, right here. Carbon, hydrogen, 413. Right? Chlorine, chlorine, that's this one here, 242. 242. All right, on the other side, we've got carbon, chlorine, 328, that's right there. And the hydrogen chloride bond, right, 431, that's where we get this 431. So add these two together and add those two together, and you get, when you add these two together, 413 plus 242 gives you 655. When you add 328 and 431, you get 759. Then now subtract these two, and the answer is negative 104 kilojoules. So the reactants are 104 kilojoules lower in energy level than the products are lower by 104 kilojoules than the reactants were initially. Okay. All right. Also, here's a chart that shows you the bond lengths for a number of different molecules, and look for a pattern here. Pause this, look for a pattern, come back. Alright, the pattern that jumps out at you most is that when you've got an increase of bonds between two atoms, like look at here, you've got carbon, a single bond, a carbon-carbon double bond, a carbon-carbon triple bond. Look what happens to the bond length. The bond length gets shorter. That makes sense because you got more, electrons gluing this thing together. So they're going to be held more tightly, right? Same thing here with nitrogen. 1 bond, 1.47, 2, 1.24, 3, 1.10, all right? Okay, so that brings us to the end of using bond enthalpies to calculate the overall change of enthalpy in a reaction.